Hi guys, welcome to my YouTube channel, Learning Physics with IBM, and today I gathered the courage to record another paper 5. These are solved past paper questions. I'm trying to solve papers from Cambridge A-level physics. This is May, June 2023. This is paper 5.1. This is not an easy task to solve paper 5 on video. It is not really very easy because it involves drawing a graph, plotting a graph, which is really very hard. But I'm trying my level best to at least give students an insight into how to solve paper 5. So without wasting time, I would like to take you to the question paper. So this is the question paper, Cambridge International AS and A level. This is paper 5, Planning, Analysis and Evaluation. And it is 970251 May June 2023. The paper is supposed to be 1 hour and 15 minutes, but because I'm doing this on a computer, I may use more than 1 hour and 15 minutes. So I know you will bear with that because all I need is students to understand how to approach this paper. So you can print the paper and follow the video, which will be more useful. This paper is 30 marks. Each question is 15 marks. So let's start. A wooden cube of mass A is placed on an inclined plane. The cube is attached to a cylinder of mass B using a string over a pulley. So when I look at this diagram, I must find something which is going to support this plane here. So some students may want to put their block, but remember you may need to change the angle theta by raising the plane. So you need to put, if you put a block, it means in your explanation you'll be adding blocks to raise the plane. But if you are an experienced student, then you may just look for a ratchet. If you know what a ratchet is, a ratchet can be adjusted. So I will use a ratchet here, something which can easily be adjusted. So I'm doing the skeleton of my plan. So this is a ratchet. It has something which can be moved to any of these holes so that you adjust the height. So this is the ratchet I'm talking about. This is the ratchet. Okay, so I can just move these to different holes to make the angle theta reduce or increase. Okay, the angle between the plane and the horizontal surface is theta. So of course it means I know I will measure this angle using a protractor. So I've started drawing the skeleton of what I'll put in my S. So I know I'll find this angle using a protractor. Initially the cylinder is held at rest. So what will I use to hold the cylinder at rest? So I may hold the cylinder using a set square along the plane. I may hold the cylinder using a set square along the plane so that it doesn't slide. When I want to release the cylinder, the cube, I may just remove the set square. So it depends on where you put the set square because you want to release the cube so that the cylinder hits the ground. So you may not put the set square there. You may hold this with the set square above. So I may put the set square somewhere here. So I may hold the cube with a set square, and when I want the cube to move, I may just remove the set square and release the cube so that the cylinder moves and hits the ground. Okay, then the cylinder is released. The time for the cylinder to fall a distance d is t. So I will need to measure the distance d through which it falls, and this distance will be measured using a ruler. So I will need a ruler. I will need a meter ruler which automatically must be clamped. So I'll need a meter ruler which must be clamped. So I need a clamp. In other words, I will need a clamp somewhere. I'm still drawing the skeleton of this experiment. Then to measure T, you have two options. You can measure T using a stopwatch, or you could use light gates with a timer, but I'll use a stopwatch. I'll just talk about light gates. Using light gates which have a timer, or you can use a video camera with a timer in view so that you record the fall of this cylinder in order to determine the time. So I will need a ruler, and of course because I don't want the cylinder to be deformed, I want its mass to remain the same, then I may put here a sand tray so that it falls in a sand tray or a cushion. I may put a sand tray here or a cushion. This could also be for safety. I may put a sand tray here, so or a cushion. So this is a sand tray or a cushion because I don't want to fall and roll, which could cause a health problem or a safety problem. Okay, so we have to first of all choose which one is going to be independent and which one is dependent. Of course, T is going to be the dependent variable because there is no way I will change T myself as the experimenter. But I can change theta, and when I change theta, I expect that T will change. So it means the theta is going to be the independent variable because I can change it as an experimenter by adjusting my ratchet. And then T is going to be the dependent variable which will change if I change the angle theta. Okay, because if I change the angle theta, theoretically, of course, it means the gravitational potential energy is going to change, so the kinetic energy of the cube is going to change, which will affect the speed with which the cylinder falls through the same distance d. So I have to keep d constant. I must ensure d is constant because I'm not investigating variation with d, so d should be kept constant. So this is a control variable. But also I should ensure that the masses, they said what is A and B. A is the mass of the wooden cube and B is the mass of the cylinder. So these cylinders should also be the same. So A and B should remain the same because the cylinder could fall and its mass slightly changes. Maybe some parts break off or the cube. So I should always ensure that A and B are the same. Okay. Then, so I've finished to choose the independent variable, dependent variable, and I have an idea of how I will measure theta. And how will I measure t? T, I will use a stopwatch. Of course, I will repeat and obtain the average. That is, remember I told you in the previous example, you measure, you vary, you improve. So how will you measure the quantity? Normally, the independent variable is the one which you measure, vary, and see if you can improve it. If there is no way of improving it, then it's still fine. But for t, we can measure, but we may not vary t. It will vary on its own. And how will I improve it? I repeat the experiment and obtain an average value. Okay, then of course to measure the masses, I'll use a balance. It can be top pan balance or it can be an electronic balance. Okay, then H and K are constants. Plan a laboratory experiment to test the relationship between T and theta. So T is the dependent variable and theta is the independent. Then draw a diagram showing the arrangement of the equipment. I will draw the diagram. Explain how the results could be used to determine the values of H and K. So first of all, I have to see which graph am I going to plot. So I must look and make sure that what should be on the x-axis is on the x-axis I must have the independent variable. On the y-axis I should have the dependent variable or something related to the dependent variable. So from this expression here, I will take d the other side, 2d the other side, I remain with 1 over t squared being equal to minus ah divided by 2d into a plus b times sine of theta plus minus ka divided by, remember I'm dividing everything by 2d, so this will be 2d into a plus b. So I can plot a graph of 1 over t squared. Remember, t was the dependent variable, so it can be on the y-axis. Normally, when we plot a graph, we prefer to put a dependent variable or anything related to the dependent on the y-axis and anything related to the independent on the x-axis. So on the independent, we don't have theta, but we have sine theta. So I'll plot 1 over t squared against sine theta. And if you compare this equation with y equals to mx plus c, you will notice that the gradient is going to be equal to negative ah divided by 2d into a plus b. But they wanted h. How you find the value of h? So h is going to be the gradient times 2d into a plus b divided by a. There's a minus somewhere. Then to find k, notice that the y-intercept, when you compare c and this, the y-intercept is going to be equal to negative k a over 2d into a plus b. So this means k is going to be negative of the y-intercept, or 2d into a plus b times the y-intercept, then divide by a. That will be k. So you will have finished to do the analysis. Of course, this is going to be a straight line because, but not through the origin. So this is going to be a straight line, not through the origin because it has a y-intercept, not through the origin because it has a y-intercept. Okay, then so we have finished to see which graph would be plotted. Then how about to be safe? For safety, most likely the cylinder could fall and maybe hit your legs, hit you when you're doing the experiment. So in order to avoid that, I've put a sand tray, or it could roll and you step on it and fall down. So I have put a sand tray so that it just hits into the sand, or you could put here a cushion for safety. So you could put here a cushion for safety. So so that is the skeleton of my experiment. If I have the skeleton at the back of my mind, now it becomes easy for me to write the plan. So let's start. I'll start this time. Let me start by stating the independent and the dependent variable before I draw the diagram. So I'll say in this experiment, in this experiment, so theta is the independent variable and t is the dependent variable. And t is the dependent variable. So what will I keep constant? I said I will keep d constant. I'll also ensure that a and b are constants. So I will keep d constant. I will keep d constant and also keep a and b constant. Of course, I have to explain to the examiner how I will keep d constant and how I will ensure that a and b are always constant. I will explain that in the further explanation. So to collect and analyze data, I'll have to set up. So to collect and analyze data, To collect and analyze data, I will take the following steps. Okay, so the first step, I have to build an experimental setup, and I have to show this in the diagram. So let me first draw the diagram of the experimental setup, because I will have to build the experimental setup as shown in the diagram, which I'm going to first draw. So this diagram is just a modification of what has been given on the previous page. So I will need a flat surface that could be a table. So I have to draw a flat surface. So for you can use a ruler and draw something very beautiful. Me, I'm just using this on a computer, so it may not look very nice. So this is the table or the flat surface. So I can call this one the bench or the table. Okay. So one, I need to put the plane. So I'll begin by putting a plane here. Okay, so I will need to, of course, to fix this end here so that it doesn't slide. So you could put something here to prevent this from sliding. I don't want to make it very large because I need this space for the protractor. But you need something to stop this from sliding. Then I'll have to add a pulley. Okay, then so here I will have a protractor because I'm going to measure this angle. So I'll just draw something like a protractor. Remember, this angle should be theta. So I'll put a protractor here. It's hard for me to draw a protractor. This is not nice at all. Okay, I think that is good enough. You can draw a better diagram for a protractor. So of course the origin of the protractor should be at this point here. So I just want to show that this is a protractor. You can do something better to represent a protractor. I will just label this as a protractor. Okay. So remember, this angle is going to be theta. So that is theta, but I'll be adjusting that angle. So I decided to put a ratchet. So I'm drawing now a ratchet here. So this is a ratchet. So it should be having an adjusting knob. Okay, so this is the ratchet. Of course, you could have used the blocks where you go on adding blocks to raise the height, but me, I've decided to use this one because this is easy to adjust. So this is the ratchet. Okay, then so I will put the block and the string. So you could draw something better than mine on a paper. So here I have the cylinder, and I have to put the cube here. So this is the cube. So I have to label these also. So this is the plane. This is the cube. And this is the cylinder. This is the string. And this was the pulley. Okay, so I want also to add a set square here, which I will be holding. I'm just showing where they will put my set square so that I can just release it in case I want to release. I can just move it in case I want to release this cube. So I'll just show here protractor. Even if I don't show the protractor here, but I just wanted to add it there because it makes my diagram look even more detailed. Not protractor, set square. So this is my set square. So that is the position of the set square. So what is remaining is measuring D. So D is going to be the distance up to the down here. So down here, I'm going to put a sand tray because I want this to fall in a sand tray. So I didn't put enough space here, but it's fine. So here I have a sand tray. So this is a sand tray. Okay, then so D is going to be the distance through which this falls. This distance I'll call it D. It must be measured using a meter ruler. So this is going to be D. So I'm going to add a ruler, a meter ruler here, but the ruler should be clamped. So okay, so I have to clamp this ruler, so I must add a clamp here. I must add a stand and a clamp. So this is my stand. So this is a stand, and I should add a clamp. This is a meter ruler. So this is the clamp. Okay, I think my diagram is complete. It is more detailed. I think I've added everything, and this diagram would give me about 4 marks, I think. Without even any explanation, I can have 4 marks. One, I've showed how I'll be changing the height, the angle theta. I've showed a protractor. I've showed how I would be releasing the cube. I've showed how I would measure the height, the distance d with a meter ruler, which has been clamped. I've even given an additional detail because I put a sand tray at the bottom. So I have many marks here. Even if I don't write about the sand tray in the essay, I'll get the mark. Even if I don't write about the meter ruler in the essay, I'll get the mark. Even if I don't write about the ratchet in the essay, I will still get a mark because it will be seen in the diagram. Note that I may use light gates. This is just an addition. Anyway, I'll talk about that later on. But let me talk about it here. This is not part of this diagram, but to measure t, instead of using a stopwatch, I may put light gates. And for light gates, they must be connected to a timer. I'll use red because this is not part of this diagram. It is just if you want to use, instead of using a stopwatch, you want to use light gates. So if you want to use light gates, then you will draw 2 light gates. But these should be connected to a timer. So you will tell the examiner that this is a timer, and you tell the examiner that these are light gates. Of course, the best thing to do with them is to clamp them. You would clamp them. So it means you would clamp the light gates. You put them on a clamp. So you would show the beam of light, but this time d would be the distance between the light gates. It will not be the distance from the bottom of the cylinder up to the sun tray, because d will be the distance when the cylinder crosses the first light gate, the timer starts, and when the cylinder crosses the second light gate, the timer stops. I'm saying this is in the place if you don't want to use a stopwatch. So this is in place of a stopwatch. If you don't want to use a stopwatch, you would add an additional diagram of light gates. So as simple as that. But I'm going to concentrate on using a stopwatch. So let me continue. So I have finished to draw the diagram. So I'll say I'll build the experimental setup. So I will build the experimental setup as shown in the diagram. So I'll build the experimental setup as shown in the figure above. So I will first of all measure theta using a protractor. I will measure theta using a protractor. Okay, I will measure theta using a protractor, and I will measure of course I will measure A, the mass of the cylinder, and the mass of the cube using top band balance or an electronic balance. I will measure A and B, those are masses, using a top band balance. So now I'm about to I have to put this I have to put the cube and the cylinder onto the plane. So I will hold the cube. I will place the cube on the plane and hold it using a set square, and hold it using a set square. So then record D from a meter ruler. So, and then record D using a meter ruler. So it means while holding the cube on the plane, I will now look at the meter ruler and record the distance D of the cube above the sun tree. Okay. So next, this be 5. Of course, I must ensure that D is large enough because I want to find a large value of T which has a smaller percentage uncertainty. So here I must mention and say I will use a large value of D so that T is large enough. So T is large to measure with a small percentage uncertainty. So when you take a measurement of a large quantity, you have a smaller percentage uncertainty. So D, so that T is large to measure. If T is large, then the percentage uncertainty is smaller. Okay. Then 6. Now I'm going to I must release the cube so that I determine the time T. So I will now move this. Move the set square. I will now move the set square. Will now move the set square to release the cube, and start the stopwatch. At the same time. So I will now move the set square to release this cube and start the stopwatch at the same time to determine the time T it takes to hit the sand. So now I'm finding the time it takes to hit the sand. So I'll now move the set square. When I remove the set square, the cube starts sliding upwards, and as the cylinder moves down, so I determine the time it takes to hit the sand. Okay. And I am saying that in this position, I would have used, let me put in brackets, I would have used the light gates. So here I'm putting this in brackets. I would have used light gates. I would have used light gates, 2 of them, with a timer. And I'm saying if you use light gates with a timer, it means D would be the distance between the light gates. So D would be the distance between the light gates, but still it will be measured with a ruler. Okay, then step number 7. So I have now to repeat experiment 6 so that I get, since I'm using a stopwatch, I'll have to repeat experiment 6 so that I have an average value of t. So I will repeat step 6 for the same value of theta. For the same value of theta and obtain an average value of t. And I will obtain an average value of t. So step 8. Now the next step is now to adjust the ratchet so that I change theta so that I can now find different values of t. So I will adjust the ratchet. If you're using blocks, you would say I will add more blocks to change theta, or remove blocks to change theta. So I will adjust the ratchet to change theta. And also, remember I have to keep d constant, so I have to adjust the length of the string so that it is constant. And also adjust the length of the string so that the cylinder is always at the same height from the sun, is always at the same height from the sun. So here I'm saying I'm trying to ensure that d is constant. D does not change. So you have always to ensure that adjust the length of the string so that you put d to the you put the cylinder at the same height above the sun so that d remains constant, because we are not varying d. If d varies, then it means t is going to be varying, yet we're investigating only theta and t. So next, now I have, by the way, I also have to check the masses A and B. I'll also check, I will also check that masses A and B have not changed using a top band balance. So of course, if the masses change, the speed is going to change. So the time will automatically change. The weight changes, the speed changes, the time automatically changes. So if the cylinder hits the sun, small part may break off. So you have to check and see that the mass has not changed using a top band balance. So number 10 is now just repeating. So I will repeat steps 2. Step 2 was measuring theta. So yes, I will repeat step 2 to step 9 to step I will repeat step 2 to step 7, I think. I will repeat steps 2 to 7 until I have 6 sets. 6 sets of values, or 6 sets of results. So now that I have 6 sets of results, the next thing is to plot a graph. So I will plot a graph. I'll plot a graph. We have already seen which graph we shall plot. So I'll plot a graph of 1 over t squared against sine theta. And we have seen what the graph would be like. So if the graph is a straight line, if the graph is a straight line, not passing through the origin, not passing through the origin, because it had a y-intercept. So if the graph is a straight line not passing through the origin, then the relationship is valid. Then the relationship is valid. Then it told us to explain how we shall find h. So we can, since we have already analyzed this on the first page, so I'll simply say h is going to be equal to minus 2d, I think it was minus 2d into a plus b times the gradient, then divide by a. And from our analysis on the first page, we also saw that k is going to be equal to minus 2d into a plus b times the y-intercept, divide by a. Then the last thing is just for safety, so that we'll call this one 12 for safety. So the safety precaution, the marker could be given on the diagram because I've already added the sand tray. So for safety, I will place a sand tray, or you could put a cushion below the cylinder. To prevent damage to the floor or injury in case it rolls on the floor. Okay, so that is for safety. So this is how I would present my work, how I would present my plan if I was answering this question. So you can look at my diagram, and from the diagram, remember this part here, I said in case you don't want to use a stopwatch to measure time, you would add light gates. In this experiment, theta is the independent variable and it is the dependent variable. I will keep D constant and also keep A and B constant. To collect and analyze data, I will take the following steps. I will build the experimental setup as shown in the figure above. I will measure theta using a protractor. I will measure A and B using a top hand balance. I'll place the cube on the plane and hold it using a set square and then record D using a meter ruler. I will use a large value of D so that T is large to measure with a smaller percentage uncertainty. I will now move the set square to release the cube and start the stopwatch at the same time to determine the time T it takes to hit the sand. I will repeat step 6 for for the same value of theta and obtain an average value of t. That is very important. I'll adjust the ratchet to change theta and also adjust the length of the string so that the cylinder is always at the same height from the sand. I'll also check that masses A and B have not changed using a top-down balance. So every time after every trial you check. I'll repeat steps 2 to 6 until I have 6 sets of values. I'll plot a graph of 1 over t squared against sine theta. If the graph is a straight line not passing through the origin, then the relationship is valid. So they wanted us to state how we can find h and k. So we had already analyzed this on the first page. So h is equal to that and k is equal to that. And for safety, I will place a sand tray or cushion below the cylinder to prevent damage to the floor or injury in case it rolls. Rolls is double L. In case it rolls on the floor. So that is my planning. So if I have delayed, you are supposed to use about 30 minutes for that question. I would use 30 minutes if it was on paper. Question number 2. A student investigates the discharge of capacitors in the circuit shown. Okay, I will not look at that. I'll just go straight here. A graph is plotted of t on the y-axis against c on the x-axis. So I must make sure anything related to t is the subject. So if I make t the subject from this equation here, it means t is going to be the minus goes to the left. So it will be minus c and r come this side. So it's minus cr ln of v divided by v naught. So it means t is equal to minus r ln of v divided by v naught times c. So because the graph is plotted of t against c, if I compare with the y equals to mx plus c, on the y-axis I have t, on the x-axis I have c. So you see that the gradient is negative r ln of v naught, of v over v naught. So the gradient is negative r ln of v divided by v naught. Okay. So values of Cp, Cq, and T are given. So T is time, I think. The discharge of the capacitor is repeated and the mean T is calculated. So T is T1 plus T2 divided by 2, which means the uncertainty in T is going to be half of the range because of repeated measurements. The uncertainty in T is half of the range because T is got from the average, so it's half of the range. Okay, so let's check the values here. So the relationship between C, Cp, Cq is given by this one here. So it's the product over the sum, which is like a resistance in parallel. So I'll just press my calculator. It is Cp times Cq divided by Cp plus Cq. So I'm going to ignore the power of 10 because it has already been compensated for. This would be times 10 power minus 4 times 10 power minus 4 divided by 10 power minus 4. One of them cancels, so we remain with this one, which has already been put in the column of the table. So I'll just press my calculator. So for the first one, it is 2.2 times 1.5 divided by 2.2 plus 1.5. Remember to maintain the same number of significant figures or more. So this will be 0.8 I'll write more significant figures. So this will be 0.89. When you round off to 0.892, because the 891 is recurring, so it is 0.892. The next one is 2.2 times 3.3 divided by 2.2 plus 3.3. So that is 1.32. Then the next one is 2.2 plus 5.6 divided by 2.2 plus, 2.2 times 5.6 divided by 2.2 plus 5.6. So this is 1.58. The next one is 3.3 times 1.5 divided by 3.3 plus 1.5. So this is 1.03. The next one is 5.6 times 1.5 divided by 5.6 plus 1.5. So this is 1.18. And the next one is 5.6 times 3.3 divided by 5.6 plus 3.3. So this is 2.08. Okay, so that is C. Then calculate and record C and T. So we have to find T is the average. So T is simply the average. So 12.9 plus 14.5 divided by 2. So there are three significant figures. I can maintain three significant figures. So this will be 13.7 plus or minus. The next is 21.1 plus 19.7 divided by 2. So this is 20.4 plus or minus. The next is 23.7 plus 24.9 divided by 2. Remember, for repeated measurements, we get the average. That's why I'm summing up and dividing by 2. So this is 24.3 plus or minus. The next one is 15.3 plus 16.9 divided by 2. So this is 16.1 plus or minus. The next is 19.0 plus 17.6 divided by 2. So this is 18.3 plus or minus. The next is 30.9 plus 32.1 divided by 2. So this is 31.5 plus or minus. Okay, so let's also find the uncertainty. Of course, the uncertainty is going to be half of the range. So for the first one, you just subtract, don't mind about the negative, just minus and divide by 2. So I can even say, okay, 14.5 minus 12.9 divided by 2. That is plus or minus 0.8. So this is 0.8. The next one is 21.1 minus 19.7 divided by 2. So this is plus or minus 0.7. The next one is 24.9 minus 23.7 divided by 2. That is 0.6. So the next one is 16.9 minus 15.3 divided by 2. That is 0.8. Then the next one is 19 minus 17.6 divided by 2, so that is 0.7. And lastly, 32.1 minus 30.9 divided by 2, so that is 0.6. So those are the uncertainties in T. It is just half of the range. The uncertainty here was half of the range. That is the highest minus the lowest divided by 2. That is the uncertainty for repeated measurements. Okay, then plot a graph of T against C. So I have to record these values on paper so that plotting becomes easy for you. If you have printed the question paper, it is very easy. Just look at them directly. So I'm going to plot T. So I'll have to record T values on paper. And I have to record the C value, the corresponding C values. Okay, so now I'm going to plot a graph. The scale here is chosen. All you need is to verify the scale. So on the x-axis, I'll check the scale on the x-axis. On the x-axis, the scale is 1 minus 0.8 divided by 10 small squares. So each small square is 0.02. On the y-axis, we have 14 minus 12, that is 2, divided by 10, that is 0.02 on the y-axis. So let's plot. This graph, okay, remember how we plot? The point should be very small, and the circle should also be very small. The purpose of the circle is to make the point visible. Okay, so the first point is, if you have printed the question paper, it is easy to follow. The first point is on the y-x-axis, it is 0.892. So this is how I will put that point. I'll say 0.892 minus the origin, which is 0.8, divided by the scale, which is 0.02. So this means I'll add 4.5 small squares. That is approximately 4.5 small squares. So 1, 2, 3, 4. Approximately in the middle of this box. Against on the y-axis, I have 13.7. So 13.7 minus 12 divided by the scale on the y, which is 0.2. So that means I need 8.5 small squares. So 1, 2, 3, 4, 5, 6, 7, 8.5. So the point must be in the middle of the box. It must be in the middle of this box. So I will draw a small circle around the point. Okay. Then the next one is on the x-axis is 1.32. 1.3 is after 1.2, so I'll say 1.32 minus 1.2 divided by the scale on the x-axis, which is 0.02. So I must add 6 small squares on 1.2. So 1, 2, 3, 4, 5, 6 should be around here. Then the y value is 20.4. So I have 20.4 minus, where is 20 supposed to be? 20.4, so it is minus 20 divided by the scale, which is 0.2. So those are 2 small squares. So on 20, I add 2 small squares. So on 20, I'm adding 2 small squares. Remember, these were 6, 1, 2, 3, 4, 5, 6. Then I added 2 small squares. So this is the point. To make it visible, I'll just circle this. Your circle should be very small. It is hard to just draw it on a computer. Then the next one is on the x-axis is 1.58. So I have 1.58 minus 1.58 is close to 1.4. So I'll say minus 1.4. Then I divide by the scale, which is 0.02. So I will add 9 small squares on 1.4 to reach 1.58. Those are 9 small squares. Then on the y-axis, it is 24.3. So on the y-axis it is 24. Remember on 1.5 I'm adding 9 small squares to reach 1.58. Then on the y-axis I have on the y-axis I'm plotting 24.3. So minus 24 divided by 0.2. So that is 1.5 small squares. So on the y-axis, on the x-axis, I'll add 1, 2, 3, 4, 5, 6, 7, 8, 9. Then on the y-axis, I add 1.5. So the point is here. And I'll circle this point to make it visible. Then the next point is on the x-axis is 1.03. 1.03 is in between here. Remember, each box here is 0.02. So I'll say 1.03 minus 1 divided by the square, which is 0.02. That is 1.5. So I add 1.5 on 1.0 to reach 1.03. Then on the x-axis it is 16.1 on the x-axis. So that is 16.1 minus 16 divided by 0.02. 0.2 on the y-axis. So that is half a square. So on 16 I'll add half a square. So the point is going to be this one here. It is in the middle of the box. So I'll circle this to make it visible. It is in the middle of that box. Then the next point is 1.18. 1.18. So I'll say 1.18 minus 1 divided by the scale, which is 0.02. On the x-axis, those are 9 small squares. Then on the y-axis it is 18.3. So 18.3 minus 18 divided by 0.2, those are 1.5. So 9 small squares from 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Then 1.5. This is 1.5 small squares on the y. So 1.5. So this is the point in between here. It is in between the small square, in between the squares. So I'll make it visible by circling it. Then the last point is 2.08. So 2.08 I think is very easy to tell. 2.02, 04, 06, 08. Those are 4 small squares against 31.5. 31.5 minus 30. The closest here is 30. So minus 30 divided by the scale, which is 0.2. Those are 7.5 small squares. So I counted 4 from here. 1, 2, 3, 4. That is 2.08. Then I count 7.5. 1, 2, 3, 4, 5, 6, 7.5, which is here. So it is in the middle of the box. So I'll circle this point to make it visible. Yeah, so plotting on a computer is not easy, but I've tried my level best. So I have to draw the line of best fit. So I'll try to, you will bear with me, I have to make this to look smaller so that it fits on one graph, because the line of best fit requires judgment using a ruler. So I have to fit the graph on one page. So I can try to make it bigger, but it should fit on one page. Okay, So when you're drawing the line of best fit, you make sure the points are balanced, and you make sure that the line goes through most of the points. If not, then the points above and below the line should be the same. The line can extend beyond the plotted points. Don't always aim to join the last point and the first point, but you try to balance your points. So it is hard for me to draw a line on a computer unless because I don't have an electronic ruler, but I will try to this is just for guidance. No, this is not a better line. At least I have to rub this. The line shifted to the left, so yeah, I think I will take this one. You can draw a better line than mine because me, I'm using a computer to draw, so your line should be better than mine. Let me try the third attempt to draw another line. So that the ruler shakes on the computer. No, this is worse. Yes, at least that is better. That is better. Okay, so that is my line of best fit. It may not be the best line because I'm drawing it on a computer. You could draw a better line. So next is I'm going to draw the error bars now. So the error bars, for the error bars, I can expand the graph. So the error bars, I will just also write them on paper so that I don't always keep scrolling backwards to check on them. So I have 0.8, 0.7, 0.6, 0.8, 0.7, 0.6. Okay. So the error bars, because the error bars are for T and T is on the vertical, the error bars are also going to be vertical. So the first error bar was 0.8. Remember the scale on the y-axis is 0.2. So 0.8 0.8 divided by 0.2, how many squares are those? 0.8 divided by 0.2. Those are 4 squares up, 4 squares down. So from the center here, we have a half, 1, 2, 3, and a half to make it 4. It should stop in the center here. So I'll draw this. The error bar should be here in the middle of the box. Then half, 1, 2, 3, and another half to make it 1, to make it 4. So it stops in the center here. That is 4 small squares above the plotted point and 4 small squares below the plotted point. That's why it stops in the center here, because the plotted point was in the center. So that will be the error bar. It is hard to draw it on a computer, to make it neat when you are drawing. So for the error bar, I have to increase the weight so that they look so nice. Okay, that is fine. In an exam, you can pass there the pencil twice to make it look nice and bold. Okay, the next error bar is 0.7, that is 3.5, I think. 0.7 divided by 0.2, that is 3.5. So this point is also in the middle of the box, so I have to just add 3 above and 3 below. So it is a half, 1, 2, 3. So this will be around here. and also a half, 1, 2, 3. So this will be around here. Then I'll draw the vertical line. It should be in the middle of the box. Mine slides when I draw the line. It kind of slides. Okay, so that is the error bar. Then the next one is 0.6, which is 3 above and 3 below, but the point was in the middle of the box, so I'll just add 2.5. So a half, 1, 2.5. So it is 1, 2.5. So this should be in the middle of this box. It is a half, 1, 2. It is 3.5. So a half, 1, 2, 3. It is already a half, so add 3 boxes. A half, 1, 2, 3. So this is along this line here. A half, 1, 2, 3. So it should not be in the center, it is along the line because it is 3.5 small squares. A half, 1, 2, 3. So it's along here. Then I'll draw the vertical bar. Okay, then the next error bar is 0.8, that is 4 above and 4 below. 1, 2, 3, 4. This is direct. Then 1, 2, 3, 4. Then I draw the vertical error bar. Then the next one was 0.7, which is 3.5 small squares, but there's already a half there because the point is in the middle of the box. So we have a half, 1, 2, 3. So this would be here, a half, 1, 2, 3. So that is there. This vertical line is going to be here. Then the next one is, or the last one is 6, which is 3 small squares, but the point was in the middle of the box. So 3 small squares, it means I count on I will add it 1.5. So a half, 1, 2, and another half. So the 3 will be in the middle of the box. A half, 1, 2.5 to make it 3. So it is in the box. When the error bar is half is in the middle of the box, the examiner will be very careful about that, so that because he knows students already put it along the box or along the line, the grid lines, which is wrong. Okay, so my error bars are done. Next, I'm going to draw the line of worst fit. That one, I'll just even change the color of the. I can change the color. Even the exam, you can use a pen for the line of worst fit because that one, you just make a single judgment. So to draw the line of worst fit, I have to fit the points on the same space. So there are several methods. I will draw the steepest line where you can join the top error bar to the bottom error bar, but check that all the vertical lines of the error bars are crossed. If they are not crossed, then you have to change the method. So if I try that method, let me see. I'm starting with the top error bar and the bottom error bar. And it's like the second last error bar at the bottom is not well crossed. So I adjust to it. I'm adjusting to the second last error bar so that it is well crossed. So I can now do my line. So you notice that if I had not done that, the second last error bar would not be crossed. But I adjusted the line so that it is also crossed. So that is going to be my line of worst fit. So this will be line of worst fit, the other one is line of best fit. So now I have to label these lines. So this is worst fit. And the one in blue is best fit. I didn't want to label below the lines because I'm going to do a triangle. Okay. So the next thing is to find the gradient. So I must do a triangle for the gradient. So let me go back to, because here I'm using a pencil. Let me use another color for the triangle so that is visible to people. I'll use purple. So when you're choosing the points for the triangle, you choose points where the grid lines completely cross the line, or the line completely crosses at the center of the grid lines. Your line that you have drawn is exactly at the center of the grid line, so that reading the points is very easy and direct. So I'm looking for those points. These lines might not be perfectly straight, like you can see here, but for you can draw a straight line. This is just a guiding tool. So I'm looking for points where the grid lines cross exactly. So I'm just going to take an estimate value of, because it is hard because the lines are not perfectly straight, I'm just going to choose an estimate value, or a value which is very close, and I say it is at the center. So for instance, this line is not very close to the center, but I want to take this point. I want to take this point and this one here, these 2 points. So if I take those 2 points for my triangle, so I'll draw my triangle going downwards. The triangle can be dotted. Make the triangle bold and visible. Then I have also to choose a pair of points at the bottom where the grid lines cross at the center. I mean the grid lines meet the lines that you have drawn. If you see it is not possible to have two points, then draw 2 triangles. So let me even draw 2 triangles in this case, so that students can know that sometimes you can even draw 2 triangles. Sometimes my computer stops. So because I couldn't find 2 points where I could draw 1 triangle, now I'm going to resort to drawing 2 triangles. So 1 triangle will be for the blue. I'll use blue for the blue triangle for the line of best fit. I'll use blue. So I choose a point where the grid lines meet this line perfectly. So I've taken that point for the triangle. So I'm choosing another point at the bottom for blue. So I'll take this point here. So this will be the horizontal line for the triangle. Okay. Then for the green one, I'll also use green for the triangle. Let me use green, the line of worst fit. I'll use green. So I'm looking for a point, so it is easy to see that this point here. So I have also to choose a point at the top where the line is, for instance, I could take this point here. You must use a ruler. Me, I'm tired of using the ruler. So now I have 2 triangles because it was very hard to find common points on both lines to draw 1 triangle. So I have 2 triangles. So I have to write out the points so that it is easier for me to use them for calculation. So here for the best fit, for the best fit, which is in blue, the x value, I have to read the x value and the y value. The y value can be seen from the graph, which is this value here. And I think that is 30, because on the y-axis it is 0. So that is 30.2, 30.4. Then for the worst fit here, I need this value, and the y value is, I can read it from here, which is this value. So 30.4.6.8, 31.2.4.6. So it is 31.6. Then the corresponding x values for blue it is 2.0, which is the best fit. So this is 2.0. And for green it is 2. Remember the x-axis, the scale was 0.02. So this is 2.020406. So 2.06. Okay, then here we have these values this side for the best fit, which is in blue. X-axis is 1.0 point, this point here. 1, 2, 3, 4, 5, 6, 7. 7 times 0.02. 7 times 0.02 plus 0.8. So that is 0.94 on the x-axis. And on the y-axis it is 14.2.4.6. Then for the worst fit, you don't write this in an exam, but because I'm doing this on the same page, on different pages on a computer, I need convenience. That's why I'm writing them here. For the worst fit, which is in green, the x-axis is 1.0 and the y-axis is 1, 2, 3, 4, 5. It is at 5, which is 15. So this is going to be 15. Now finding the gradient. So I'll have to write these points so that finding the gradient, I don't always come back to the same page. So I will have to write for best fit. The first values are 0.94 and 14.6. And for the worst fit, the first values are 1.0 and 15. Then the second values for the best fit, we have 2.0 and 30.4. Then for the worst fit, we have 2.06 and 31.6. Okay, now let's find the gradient. So determine the gradient of the line of best fit in absolute uncertainty in your answer. So since there is absolute uncertainty, I have to find the two gradients. So it's a gradient of best fit. So I'll take the best fit values. The change in your y values, we had 30.4 minus 14.6. Then the change in the x values, we had 2.0 minus 0.94. Then we have to find the gradient of the worst fit. The worst fit values, we had 31.6 minus 15 divided by the x values, which is 2.06 minus 1.0. So I remember there was a 10 power something, 10 power minus 4 on the x-axis. So I have to multiply by 10 power minus 4 on the x-axis. So the x values, I will set times 10 power minus 4 times 10 power minus 4. So let me press my calculator to find the gradient. So this will be 30.4 minus 14.6 divided by 2 minus 0.94 exponent minus 4. What is that? Answer was divided by 2 minus 2 minus 0.94. Again, divide by 1 exponent minus 4. So this is 1, 4. I'll just write 1.49 times 10 power 1, 2, 3, 4, 5. 1.49 times 10 power 5. So the second one, 31.6 minus 15, divide by, open brackets, 2.06 minus 1. I'll divide this by 1 exponent minus 4, which is times 10 power minus 4. So this is 1.57. I'll just write 1.57 times 10 to the power of 1, 2, 3, 4, 5, power 5. So the uncertainty is going to be the difference. I will say 1.57 minus 1.49 times 10 to the power of 5. So I have 1.57 minus 1.49 times 1 exponent 5. That is 800. So this is 800. No, 8,000. Okay, so here I have to write the answer as 1.49 times 10 to the power of 5. If I want to write the same number of the same power here, remember it was 0. What was that? 1.57 minus 1.49. It was 0.08 times 10 to the power of 5. These are two decimal places, so I will say plus or minus 0.08 times 10 to the power of 5, or I would write 1.49 plus or minus 0.08 times 10 to the power of 5. I would write it like that. Of course, here the number of decimal places doesn't matter. That only matters in paper in paper 1 and paper 2. Okay, so having found a gradient, now calculate ln of v over v naught, include the absolute uncertainty. Okay, so to calculate this, I think this is direct, doesn't require the results. So I'll first of all press the calculator to find ln of v over v naught. Exact values will be ln of, this will be v, which is 2.4, over v naught, which is 4.8. So that is 2.4 divided by 4.8, and I get the ln of the answer, which is negative 0.693. Okay, then because I have to include the absolute uncertainty, then I must be very careful here. So there are several ways of doing this. I'll just choose a few. You could say ln of v over v naught maximum minus ln of v over v naught. How will I make v over v naught to be maximum? V should be maximum while v naught should be minimum. So this will be equal to ln of v should be maximum while v naught should be minimum to make the fraction maximum. Then minus ln of v over v naught, which is minus 0.693. So this is going to be ln of, what is v maximum? 2.4 is exact, so plus 0.1 to becomes ln of, the maximum value is 2.5. What is v naught minimum? So I have to subtract 0.1 from 4.8, so that will be 4.7. Then minus ln of the exact value is 2.4 over 4.8. So I'll simply say ln of 2.5 divided by 4.7. This is 4.7 Then I subtract the answer which I had got before. So I'm getting this as 0.20. Is it? Let me check it again. Maybe there's wrong algebra. ln of 2.5 divided by 4.7 is that one. Then minus. Okay, so let me first write this. The answer was minus, so this is minus 0.63631 minus negative 0.693. So I will say minus 0.631 minus negative 0.693. So that is 0.06. So this is 0.062. So plus or minus. Remember, we just want the difference. So the answer here is going to be negative 0.693 plus or minus 0.062. So this is going to be the answer here. Using your answers to A, C, 1, 3, and D, determine the value of R. So this takes us to the first page. Remember, we said the gradient was equal to negative R ln of V over V naught. So I want to find R. So R will be the negative of the gradient divided by ln of V over V naught. So this would be the negative of my gradient. The gradient was 1.49 times 10 power 5. 1.49 negative 1.49 times 10 to the power 5. That was the gradient. Divide by ln of which was minus negative 0.693. So the negative cancels out. So I'll just say 1.49 exponent 5 divided by 0.693. So that is 215,000. I'll just write 215,000. Include an appropriate unit of R. So what was R? Of course, R was resistance. I just put ohm. Then determine the percentage uncertainty in R. Percentage uncertainty in R. Just look at how we have got R. So since there is division, we can use fraction uncertainty. So the fraction uncertainty in R over R is going to be, I will ignore the minus there. So it will be the fraction in the gradient divided by the gradient plus the fraction in ln of V naught over V naught divided by ln, the absolute in ln of V naught over V naught, not V naught over V naught, divided by ln of V over V naught. And of course, this, I can multiply this by 100, even this side by 100 to make it percentage. So this is going to be, for gradient, it was, what was for the gradient? It was 0.08 divided by 1.49. So this is 0.08 divided by 1.49. I don't need to add times 10 power 5 because it will cancel out. Plus, for the ln, it was 0.062. 0.062 divided by ln of V over V naught, which is 0.693. I don't need to consider the minus because it cancels out. Then I'll multiply this by 100 to make it percentage. So from my calculator, 0.08 divided by 1.49 plus 0.062 divided by 0.693. Then I will multiply this by 100 So this is going to be 14.3%. And finally, the experiment is repeated. Determine the value of C that gives a value of t 60 seconds. Include the absolute uncertainty. So this also takes me back to the original equation. I have to make C the subject. Remember, it was ln of V over V naught equals to minus T over CR. So I make C the subject. So C is going to be equal to minus T divided by R ln of V over V naught. So this is going to be minus T negative 60.0 divided by R. We have got R as 215,000. Then times ln of V over V naught. We got this one in part D. In part D, it was negative 0.693. Somebody may ask here, maybe because I've not added the times here, so let me add it. People would see this is times 10 power 5 times 10 power 5, it cancels out. This was plus or minus, this was negative. Of course, the signs here do not affect the values here. So that's why I didn't put a negative on 0.693. I just needed the magnitude. But here it is very important. This minus here cancels out the other one, so that this will be minus 60.0 divided by negative 0.693 times 215,000. So the negative has cancelled. I have 60 divided by open brackets 0.693 times 215,000. So this is equal to 0.0004 0, 2 or 0.3. Of course, the capacitance must be very small. That's why it is always recorded in microfarads. So it makes sense for you to get this as 4.03 times 10 to the power of 1234 power minus 4 farads. So this will be the final answer here. We are not supposed to get exactly the same answers. Remember, I went on rounding off the number of significant figures, so the answer will not be exactly the same, but it will be very close. Until next time, I think you have learned something from this paper. You might have revised how to deal with uncertainties for logarithms. In case of anything that wasn't clear, you can always reach out to me. Until next time, bye bye, stay blessed.